Welcome to the AI Research Roundup. I'm Alex, and today we're looking at a paper from the Hugging Face trending list, published on July 14th, 2025, just yesterday. This paper shows that even state-of-the-art models like GPT-4o struggle with embodied tasks, achieving success rates below 20%. The paper is titled EmbRACE-3K, Embodied Reasoning and Action in Complex Environments, and it introduces a new dataset and fine-tuning method that dramatically improves these results. The authors created this new benchmark to test how well models can navigate and interact in complex, photorealistic worlds. Also, the authors shared their work on GitHub. In the repository, you'll find a really detailed overview of the EmbRACE-3K dataset, including how it was constructed and the reasoning skills it benchmarks. The full dataset and code are listed as coming soon, so it's definitely one to watch. So, this first figure really illustrates the core of the EmbRACE-3K dataset. It's built on over 3,000 tasks and 26,000 decision steps. And the key innovation here is how each step is broken down. For a given task, like go near the table, then the window, the agent doesn't just see and act. It also generates a natural language rationale. Essentially, its internal thought process, like, I need to turn right to face the table. This stepwise reasoning, which links perception to action, is what's designed to teach these models to plan. To really put their contribution into context, this next table compares the EmbRACE-3K dataset against other major embodied benchmarks. And you can see at a glance what makes it unique. It's the only one that ticks every single box. It combines photorealistic scenes with stepwise reasoning. But crucially, it's also built for online, closed-loop interaction. Online means the agent has to make decisions in real time, and closed-loop means its actions immediately affect what it sees next, creating a constant feedback cycle, which is vital for realistic evaluation. And this next figure shows us exactly how they built this dataset. It's a 4-stage pipeline. First, they sample different agent starting points in the virtual worlds, capturing the agent's view and its 6 degrees of freedom pose, which is just its precise position and orientation in 3D space. Then, they use Gemini to generate the task instructions. After that, human players perform these tasks, providing demonstrations of the correct actions. Finally, and this is the key part, Gemini is used again to write out a rationale, the thinking process for each step the human took. So, with that rich dataset in hand, the authors then developed this 2-stage training framework to actually teach an agent how to use it. The first stage on the left is supervised fine-tuning, or SFT. This is where they simply show the model the correct thinking and action for each step, teaching it by example from the dataset. But then they add a second stage using reinforcement learning. With a method called group relative policy optimization, the model tries out different actions, gets rewards for good ones, and learns from that feedback, helping it generalize beyond just imitation. Alright, and this table lays out the hard numbers from that training framework. It compares models like GPT-4o against their fine-tuned agent on different tasks. We see metrics like success rate and also success weighted by path length, which rewards efficiency, not just completion. And the results are stark. Their final model, the QN 2.5 VL, with both supervised fine-tuning and reinforcement learning, consistently comes out on top. Especially in the out-of-domain section, which tests generalization in new environments, its success rate on exploration tasks jumps from just 3.6% for GPT-4o to nearly 31%. Drilling down a bit further, this next table breaks down performance on the most complex tasks, things like multi-stage goals, opening doors, and picking and dropping objects. We see a few new metrics here, like goal distance error, which measures how close the agent got to the target, and timeout rate, which is how often it just ran out of time. And the story is consistent. In familiar environments, supervised fine-tuning is very effective. But for new, out-of-domain challenges, that extra reinforcement learning step is what makes the difference, pushing the success rate up significantly for these tough interaction tasks. So wrapping things up, what this work really shows is twofold. First, it clearly demonstrates that today's best models struggle with complex, interactive environments right out of the box. And second, it offers a powerful solution. By combining a rich data set like EmbRACE-3K with a 2-stage training process, using both supervised fine-tuning or learning by example, and reinforcement learning, which is learning from feedback, we can dramatically boost an agent's ability to reason, act, and generalize in these dynamic worlds. That's all for this week's AI Research Roundup. Thanks for tuning in.